This is part 5 of a series on gradient boosting method. In this video, we will analyze the GBM classification algorithm. This video was produced in Korean and translated into English. My voice was generated through AI, text-to-speech. In the last video, we looked at the training and prediction process for GBM classification. In this video, we will analyze the classification algorithm expressed in a standardized format. Before analyzing the algorithm, let's first look at the formulas for odds, logodds, and the binary cross-entropy, etc. The target y is either 0 or 1, so it is a binary classification problem. The estimated y-hat is the probability that y is 1. This probability can be expressed as an odds value as follows. The denominator is the probability that y is 0, and the numerator is the probability that y is 1. The odds value can then be expressed in this way. Or, it can be expressed as y-hat like this. Taking the log of both sides of this equation gives the logodds. Logodds is expressed this way and is defined as f. The probability p can be obtained from this equation as follows. This is the formula for calculating probability p using logodds f. The probability can be calculated with this formula. This is a logistic function of f. Probability p and logodds f have the same information. You can calculate logodds f with probability p, and you can also calculate probability with logodds. P is bounded to 0 and 1, and logodds f is unbounded from negative infinity to positive infinity. The GBM learns the residuals, and the residual is also unbounded. GBM classification uses unbounded residual to estimate unbounded f, and uses f to calculate the predicted probability. The reason for doing this is that GBM classification cannot directly estimate the probability, bounded to 0 and 1, using the unbounded residual. This is a similar idea to logistic regression. Next, let's look at the binary cross-entropy formula. Regression uses mean squared error as the loss function, while classification uses cross-entropy. That is, it uses a binary cross-entropy as the loss function, where p is the estimated probability, which is the y-hat. Differentiating the loss function L with respect to the probability p is as follows. This time, we use logodds to represent the binary cross-entropy. Substitute this in place of the probability p in the formula above. This is the equation 3 on the left. If we multiply the numerator and denominator of equation 3 by this value, we get this equation. And replace 1 minus p with this formula. Summarizing this equation, we get the following loss function L. This is the binary cross-entropy formula expressed as logodds f. This formula will be used as the loss function L when analyzing the algorithm on the next page. Differentiating this equation with respect to f is as follows. And if we differentiate this equation twice with respect to f, we get this. This will be also used in the algorithm on the next page. Now let's analyze the GBM classification algorithm expressed in standardized form. This algorithm is exactly the same as the one we analyzed in the video in GBM Part 2. If we replace the loss function with binary cross-entropy, it works as a classification algorithm. Step 1 initializes model with a constant value. The initial value is the initial logodds f0. The initial logodds f0 is defined as the gamma value that minimizes the loss function L. Let's use binary cross-entropy for this loss function L. This is the equation 6 looked at the previous page. The gamma is the log odds value. Now let's find the gamma value at which this loss function is minimal. Differentiating this loss function L with respect to gamma, we get this. Here, this part is the logistic function. That is, y hat. Then we can write this equation like this. And if we solve the y hat here, it looks like this. The target y of the data used in the previous video is like this. Yes is 1 and no is 0. Here, the average of y is 4/6, or 0.67. This is the initial estimate, y hat, calculated in the previous video. Now, let's use y hat to calculate the gamma. If we solve for gamma from this equation, we get this result. Then the gamma will be 0.69. This is the initial logodds, f0, from step 1. This is the same result as seen in the previous video. Step 2 repeats the process below m times. Step A calculates the residuals for each data point. Here's how to calculate the residuals. Since the formula is a bit complicated, let's take only the first data point of the first round as an example. The first subscript is the data point number I, and the second subscript is the round number m. Now let's replace the subscripts with these values. Then we can write it like this. Here, since f(x) is f0, we substitute f0 for f. Then it becomes like this. And substitute the binary cross-entropy for the loss function L. And if we differentiate this formula with respect to f0, we get this result. This is the equation 7 on the previous page. The actual y value of the first data point is 1. And the initial y hat value is 0.67, so the residual for the first data point is 0.33. This is also the same as the result of the previous video. The residuals for the remaining data points are also calculated in this way. In step B, we fit a regression tree to the residuals calculated above. Here's the tree we created in the previous video. And we create terminal region, capital R, in this tree. The terminal region refers to leaf node. The first subscript j is the leaf node number, and the second subscript m is the round number. Step C calculates the leaf value, gamma, for all leaf nodes. Here's how to get gamma. The goal is to find the gamma that minimizes the loss function expressed in this way. X is the data belonging to a leaf node. Y is the actual target class, and the latter is the estimated value. The latter is the prediction part, expressed as the sum of the log odds of the previous round and the gamma. To find the minimum, we need to differentiate this loss function L with respect to gamma. However, since the latter part of L goes into the log and exponential functions, it is not easy to directly differentiate this equation. To solve this problem, we need to transform the loss function L into a Taylor series. The Taylor series for a two-variable function is like this. Now let's transform the loss function L into a Taylor series. The variable x corresponds to target y, and the variable y corresponds to log odds f. And a is 0. And b corresponds to gamma. Use the above equation to transform the function L into a Taylor series like this. And we use the quadratic approximation of the Taylor series. We then differentiate the loss function L transformed into Taylor series with respect to gamma. The result is like this. Solving for gamma from this equation gives the following result. Here, the result of differentiating the loss function L with respect to f is as follows. This is the equation 7, which we looked at earlier. And the result of differentiating the loss function L twice with respect to f is as follows. This is the equation 8, which we looked at earlier. Then, if we substitute this result into the equation above, the final gamma will be as follows. This is the gamma of step C and is the leaf value. In the previous video, the leaf value of each leaf node was calculated as follows. This is the formula we used. Understanding this algorithm will help you understand why the leaf values in the previous video were calculated this way. Step D updates the model. We use the gamma estimated above to update the previous log odds value f. I is an indicator function. This part is also very similar to the regression algorithm seen in the previous video, so detailed explanation will be omitted. Step 3 is the prediction process. We use the final log odds f to predict the final y hat using the logistic function. So far, we have analyzed the classification algorithm of GBM. It was a little more complicated than the GBM regression algorithm, because it uses binary cross-entropy and predicts y hat via logodds. In the next video, we will use this algorithm to implement GBM and SGBM.